All right, so our first speaker is Professor Larry Wald from Massachusetts General Hospital, and he is a leading expert on MRI physics, so I'm delighted to have him here to speak to us today. Thanks, Larry.
Great.
All right.
Thanks. Okay, well, thanks for being here this morning. It's a pleasure to start things off first thing in the morning with an introduction to MRI and MR physics. And one of the reasons I'm so excited about giving this talk and not being out on the beach taking a surfing lesson or something is that MRI methods, this is the most important talk in the course. So don't listen to all the the stuff later speakers will try to fool you. If you master technique and produce original data, all the rest will follow, as no less than Ramon y Cajal basically says in his advice to a young scientist. So getting good quality data at the start that can see something new is, in my opinion, the most important part of the game. And so why try to improve methods? By improving fMRI methods, I mainly mean go faster and see smaller structures. And we have the scale of the CSF, the lobes, the Brodmann areas. This is where we've been comfortably working for some decades in fMRI now. Our 3mm voxels kind of comfortably cover these areas. But quite frankly, it's good to push on. The cortex is only a few millimeters thick, and inside the cortex there's of course laminar structure and columnar structure, which we could probably hope to get to with fMRI. There's actually some good preliminary results showing that. Probably at the more microscopic level, not so easy with non-invasive imaging. But the other aspect that this doesn't show, this is focused on the cortex. There's also subcortical structures, which are 1mm brainstem nuclei, and et cetera, which haven't been widely probed with fMRI, that also fall in this category. And a decade of work has really improved things. I took an old image literally from about 1999 off a 3T scanner. These are 3mm voxels, and compared it to a 0.75mm single shot isotropic EPI taken from our 7T scanner. And I think you can appreciate that the resolution advance is real. It's not just a fictitious voxel, the field of view divided by the number of voxels. There's real structure that you can now see within the cortex and within subcortical structures. And it's also important that this high-resolution fMRI is accurate, because we're going to be comparing it to the brain architecture, and the brain architecture is laid out on the cortical surface for the most part. And this surface information we usually take from anatomical scans like the MP-RAGE. And this example here of an M being shown to the subject in the on the visual field that then maps directly onto the visual cortex shows that the natural organization of the cortex is best seen not on a slice. You can't really see anything on the slice. You can't see the structure very well on the folded cortex. It's really shown on the inflated cortex. And for this, we need the EPI to correspond to the anatomical surfaces we take. And there's also been good progress in this area. This is some free surfer fits taken from higher resolution data, in this case a 390 micrometer isotropic MP-RAGE at 7T. And you can see it's a bit noisy, but it finds a better surface, and you can also appreciate that the surfaces are relatively accurate from this. Well, one thing we've been doing to try to make the surfaces and the EPI align exactly, the EPI of course has more distortion, as we'll hear a lot about later in this talk, is to do an all EPI functional and anatomic scan. So if we have 0.75mm EPI, you might ask, why do we do the anatomicals at 1mm? The answer is, well, you don't have to. This is in a case of an IR prepped single shot EPI. So the EPI readout has exactly the same parameters that we'll use for the functional imaging later. And so it has exactly the same distortions. So any anatomy taken from this T1 weighted image will end up corresponding exactly with the functional images. There may be distortions in both, but they superimpose exactly, and that's the point. And so we take a T1 map by taking, say, 24 T1 recovery times. We take a T1 map, and then we just generate the T1 weighted image that FreeSurfer likes and use it to find the surfaces. It's also been very helpful to do this in the brainstem. The T1 weighted image doesn't show a lot of brainstem subnuclear structure, but the diffusion data does. So here we take a matched diffusion to our functional data, and then we can pick out brainstem nuclei and the white matter spots between them, and it again exactly corresponds to our functional data. Now I want to talk a bit about improving the temporal scale too. Here's the temporal scales of things in the brain as I see it. There's action potentials, postsynaptic dendritic currents, which of course MEG sees. They're broader, so there's more synchrony among them, and thus MEG sees them. The hemodynamic response is slower still by orders of magnitude, and this is great for synchrony. We can be sure that they all superimpose properly, but it means they're rather sluggish, and you might ask, why sample faster than about half of 6 seconds, which is a TR of 3 seconds? That would be Nyquist sampling this hemodynamic response. Well, there is other stuff out there. This is a spectrum of an fMRI time course for both a stimulus run, a visual stimulus, and just resting. And you can appreciate there's a cardiac bump out at around 1 hertz. There's a respiration around 1/3 of a hertz. And this is where the bold signal lies. And notice it's a logarithmic plot here on the y-axis. But still, integrating all of that junk all the way out means that there's still, a good bit of power in it. And if that folds into the bandwidth of interest, which is the bold area, then you'll superimpose that noise on your signal. So there is actually a TSNR advantage of sampling fast and then simply filtering out the unwanted high frequencies, preventing them from aliasing in. There's, of course, other strategies to try to remove them too. And this has led to some of the success of the simultaneous multi-slice technique, which I'll talk about at the end. Here we take, for example, 12 slices simultaneously. And so I'll draw attention to the TR. It's a whole brain coverage in about 1/3 of a second. So we are now capable of going up to 10 times faster than we're used to. 170 slices per second coming off the scanner. And that's a real breakthrough in temporal resolution. And one of the other reasons why I think we can use it comes to examining the Nyquist theorem and the assumptions made in the Nyquist theorem. Because the Nyquist theorem would have you believe that there's no advantage to oversampling a waveform. You might as well just Nyquist sample it. There's no advantage to Nyquist sampling it compared to oversampling and then filtering down to the bandwidth of interest. But if you look at a waveform like this and you look at those little spot samples, you kind of have an intuitive feel that you're missing most of the signal. There's all this stuff going on where the red dots aren't. And how can that be good? And actually this is a case where the intuition is better than the mathematical theorem, because you have to remember that the mathematical theorem makes the assumption that you're sampling all the time between the points. You don't have gaps between the samples. You're actually integrating the signal for all the time between the dwell times. It's more like this. And the way that's done on an ADC is simply called a sample and hold, where you connect a switch, you turn on the switch during the sample, and that integrates onto the capacitor. And so it's essentially measuring all the signal all the time. That's very different from what we do when we use EPI to sample a time series. If we have a 2-second TR, the EPI is actually measuring signal for about 30 milliseconds. So we measure signal for only 1.5% of the time. And you can see that this is not meeting the Nyquist criteria of sample and holding for the whole thing. It's very inefficient. So what else is holding us back? Well, there's the susceptibility in MR, and there's the good susceptibility, which is the bold effect from microscopic vessels of deoxyhemoglobin dephasing the water in and around the vessels. There's the bad through-plane dephasing, such as here you see in the orbital frontal sinuses. And there's the ugly, the distortions that you see in the EPI image that might literally cause you to place the activation into the wrong hemisphere. That would be embarrassing. So to get at those and what we can do about them, now I'm going to march through the main part of the talk, which is the physics of MRI from the water molecule, the proton spin, the signal we detect, the K-space, and what is this thing we call K-space, the matrix that we measure and then produce the image. And just some housekeeping, we're going to be talking about magnetic dipoles. You can think of the proton as a charged particle spinning. Well, a charge moving around in a circle, such as on a spinning ball, creates a little loop current. A loop current creates a magnetic field. It looks just like a bar magnet. You can think of it however you want. We'll represent it as a vector M pointing from south to north. And of course, every water molecule has its own protons, and each one of these protons has its own vector. The thermally agitated, they're actually quite randomized, only about a part in 10 to the fourth net alignment, and we'll call that net alignment this capital M. And that's all that contributes to our signal. We'll consider it as a macroscopic thing. That's very convenient. We don't have to consider quantum mechanics when you take an ensemble average over hundreds of thousands of particles like that. Then when you place a magnet in a B0 field, there's a torque on it. It tries to align it with the field. And there's also angular momentum associated with the proton. And the angular momentum makes it not want to return. It makes it want to precess around. That's the only thing that conserves angular momentum. So it's exactly like a gyroscope. The gyroscope, the force of gravity is pulling it down. The angular momentum says you can't fall down. That doesn't conserve angular momentum. You must precess around like this. With the spin, the torque is trying to pull it up. That's the only difference. It's just a reverse sign. Same equations of motion. When you get this stuff spinning around, that's when we can see it. And we see it using Faraday's law because the flux lines that thread through our coil, that creates a generator effect. So a generator is a spinning magnet and a spool of wire. That's exactly what we have. It generates a small voltage across the wire that's at the frequency it's spinning, which happens to be in the radio frequency range, about 125 megahertz for 3T. We simply see this as a voltage. So we keep track of the magnetization, and that's the key to forming an image. We break it into two components. It's spinning around. There's an XY component in the XY field that spins, that moves around in that plane. And then there's a Z component, which is stationary. The Z component doesn't contribute to the signal, but it tells you how much magnetization is stored and ready to go for the next excitation, because that's the equilibrium position, and we tilt it down with the RF excitation. The MXY component precesses at a characteristic frequency, the Larmor frequency, proportional to the field that that proton sees. And that's the amplitude and phase of that magnetization is what we're going to use to form the image. It's all about keeping track of the MXY phase and amplitude when a gradient is on. So the gradient is what we use to encode position. The magnet's very uniform, but then we turn on, say, an X gradient. It's a little trim field like this. It creates a left to right asymmetry. So in this case, the left side of the bore is in a lower field and the right side is in a higher field, explained by a very simple linear equation. That's important because remember the key equation is that frequency is proportional to B field and therefore proportional to position. So if we turn on a gradient and we measure our signal, since frequency is proportional to field and now proportional to position, we'll see this sort of histogram of frequencies present in the signal. You immediately recognize that as a projection image. It's a projection of the object because at the zero frequency, the B naught frequency, right in the center of the magnet where X equals 0, that's just a sum total of water through the center of the head. Out on the left ear, it's a sum total of water through the left ear. And in this case, that's at a lower field, so therefore a lower frequency. So frequency encoding uses this one standard equation. It's the only equation you need to know for MRI. Makes it easy for us. Frequency proportional to field. And before we turn on the gradients, the frequencies are pretty much all at one frequency. And when we turn on the gradient, now they're proportional to position, and we get this projection image. Here's what we would call the pulse sequence, what we use to sort of notate how we do this on the machine. There's the excitation, there's the signal, we turn on the X gradient, and we have our sampled points. Then we examine the frequencies contained in that time series to make that histogram. Now, one thing that happens if you have a local field gradient is, of course, it disturbs this one-to-one relationship between frequency and position. It's no longer linear. So here's a field map of a sagittal slice showing the bump, the disturbance above the frontal lobes and the orbital frontal cortex. That's from the air and the sinus. Air is paramagnetic, or oxygen is paramagnetic. The water in the brain is diamagnetic, so the paramagnetic material magnetizes and sort of cancels magnetization from the water and causes a disturbance up in the brain. And if we use a very weak gradient, then these local field gradients dominate and we get this very distorted image. So the image distortion is proportional to how long the readout's on, or the bandwidth of the image. Then there's the phase encoding step, the part that people have the most trouble understanding, how we encode the other direction with this little blip of a Y gradient. I want to spend a little bit of time on this because it's important for understanding distortions and K-space. And basically, now we're going to turn on a Y gradient, so the field's changing from the back of the head to the front of the head, nice and linear as before. But we're just going to blip on this gradient, so before the Y gradient's on, all the Y locations are at the same frequency. During the blip, the spins in the forehead will get ahead because they'll process faster, and then they'll all go to the same frequency. So if we keep track of phase, which is frequency times time, we'll see a phase shift from the top of the head to the bottom of the head that's dependent on position, and it's very easy to work out. It's the sort of slope of the phase change is the gamma times the gradient strength times the time, and we're going to just rename that quantity K. So we give a 90-degree pulse. Different positions get different amounts of phase. The stuff in the top of the head gets ahead. Stuff in the middle is our sort of reference phase. Stuff in the back of the head falls behind. If we look at that in a continuous picture from top of the head to bottom, we see this helix of phase is wound by that gradient blip. And once this phase relationship is there, it's locked in, because when the blip is turned off, everything processes at the same frequency and no more relative phase changes occur. If you have a weak blip, either small amplitude or short, you get a loose helix. Medium-sized blip, a little tighter, and a large blip, much tighter. It all depends on basically G times T, which is the area under the gradient curve. Now, how does this relate to K-space and sampling spatial frequencies? Well, imagine a sample of water in the magnet, and we do this blip. We see no signal at all, because for every position where the vectors are pointing to the right, there's another position where they're pointing to the left. They exactly cancel themselves out over many cycles. Whereas if we used a periodic sample spaced with exactly the periodicity of the helix, we would see a signal that's just as big as if we hadn't turned on that gradient blip. So here we've killed the signal from our biggest sample of water, and we've let it pass if it happens to have the right spatial periodicity. Well, spatial period is frequency. Spatial frequency is 1 over spatial period. So I'm going to stop talking about spatial periodicity and start talking about spatial frequencies, which is K. And they're related, and it's confusing because we've talked about temporal frequencies, things processing, but this is things periodic in space. That's just a little confusing point. So if we measure the phase and amplitude of the signal with that helix wound, we measure how much of the object varies with a spatial periodicity of 1 centimeter or a spatial frequency of 1 inverse centimeter. And we would simply fill in that number into our K-space matrix. We could then blip through and do this thousands of times and fill in the whole K-space matrix. And then the Fourier transform theorem tells us that this is enough to reconstruct the image of the same size. So if we do a 256 by 256 K-space sampling, we get a 256 squared image. Now we could sample like this, where we wind a helix, sample a point, turn the gradient back on and wind it a little more and sample another one, and we get 3 points. That would be very time efficient. Even better is just to do it like this, where we leave the gradient on. It's kind of troublesome to turn it on and off, and just sample the points. Now the helix is continuously tightening, and we're sampling as we go. Very efficient, and we call this frequency encoding. It's really hard to see how frequency encoding relates to that spatial histogram that I showed before, but here it is in the case-based picture, showing a little movie running through. First we wind a negative helix, then we unwind it. The central point is where we've exactly unwound the helix, and we're sampling the DC, or just a continuous level of signal across the object, and then we wind the opposite helix sense. So we get a whole line of K-space in one go, and that's frequency encoding in the K-space picture. So a standard sequence would look something like this: an excitation, then we blip on some large X and Y gradients. This winds the helix in the signal, and it winds a big negative X helix and a big negative Y helix at the same time. So the first point we're going to sample is down in the lower left corner of K-space. Then we're going to reverse the X helix and unwind it, and when the areas exactly match, we're then at Kx equals 0, and we read out a line at K-space like this. Then we're going to let T1 relaxation occur, give another excitation, but this time with a slightly smaller Y gradient, so we don't go down quite as far, and we start at this location and read off across, and then we complete this one TR at a time, one line at a time, filling in the K-space matrix. That's the garden variety flash imaging. Very laborious because you have to do one line per TR. You get a nice picture of K-space. Again, as we talked about, the resolution of the image has to do with the tightest helix you wind, therefore how far out in K-space you go, and the field of view has to do with the sampling between the points in K-space. So if you don't travel very far out in K-space, you'll get a blurry image, and if you travel further and further out, you get a sharper and sharper images. So this means that high resolution is laborious because you have to sample a lot of K-space. Another feature of the Fourier transform is you automatically get replica images. The Fourier transform theorem assumes that the function you're modeling or the object you're modeling is periodic. Therefore, it sort of enforces a periodicity. Even though we measure just one K-space matrix, we in fact get infinite copies. MATLAB very conveniently doesn't store all these infinite copies, it just gives you one. But the problem occurs if you don't give enough field of view that these copies will then overlap on one another, and you'll have this folded image problem. This is what happens when we try to go too fast and say skip lines in the phase encode direction. We'll talk about that a bit in parallel imaging if I have time. Even though a real object such as the brain, it's kind of weird to have a complex image of the head because our heads are real for the most part. So what does it mean to have phase in the image? It sounds like it's relatively unimportant because the object should have zero phase, but actually that's not true. Phase is actually fairly important. So here's a picture of me, snapped, not a very flattering one, slightly more flattering picture of a student in our lab, Kristen, and I took my Fourier transform from this black and white image. I took her Fourier transform from this black and white image, and we're going to do a simple experiment. Well, if we just reconstruct from these Fourier transforms, of course we get the same image back again. That's not very interesting. But what's interesting is if I swap her phase for my phase. So now I'm going to reconstruct an image with my magnitude in her phase and her magnitude in my phase. And the question is, what do you get? Do you get me, in which case the magnitude was the important part? Or does it follow the phase, or is it some sort of unrecognizable mess? Anybody hazard to take a guess? Well, I kind of set it up by saying phase was really important. So sure enough, it follows the phase. If you swap the phase and her phase with mine, you get essentially her picture. So you simply can't ignore the phase in K-space, even if the object is a real valued object like these black and white images are. Anyway, getting back to imaging, EPI strategies start out very similarly to the flash. a big negative X and a big negative Y helix, and then a line readout of one line by reversing the X gradient. The only difference is that then we reverse it again and blip on a little Y gradient, which takes us up one notch, and then we read out another line in the opposite direction with a negative X gradient. And we simply keep doing this blip, read, and zigzag across K-space to get all the lines in one shot. This has the great advantage that it only takes one TR period. It's, however, very slow. We call it fast imaging because it's fast, but it's slow in the phase direction. So points in the phase direction are taken 100 times more slowly than adjacent points in the readout direction. And this leads to the distortion in the Y direction. But all the excitations, there's no need to reboot it. It's fast. Physiological fluctuations tend to modulate the whole image phase, which we're going to throw away when we take the magnitude image. So the physiological fluctuations tend to not affect the magnitude of the image, and that is absolutely key for us. The key parameter for specifying how bad things are is the echo spacing. That's the time between lines. That's the time that you have in the Y direction for a nuisance phase to accumulate. Let me explain that a little bit. If we have 2 points in the brain that have different frequencies, then there's going to be a phase accumulation between them, frequency times echo spacing. That phase will accumulate in the Y direction. And this is what causes the distortions and the dropouts. Let me just quickly get to that. The dropouts are easy to understand. If you have a bunch of spins in the voxel and they each see a different field, then they each go at a different frequency, and the fast ones get ahead in phase during the readout and the slow ones get behind, and you get a net cancellation of the vectors at time TE. This is very easy to see. As you set TE longer and longer, you can just watch the dark spots develop over the temporal lobe, lower temporal lobe, and orbital frontal sinuses. One of the nicest ways to deal with this is simply to take thin slices, because then there's less of a range of frequencies through the slice. So this is our first line of defense, and now it's very rare for people to use 5mm slices anymore. And at higher resolution, we always try to use isotropic slices for this reason. And in fact, you can see from these 1mm isotropic slices at 3T that if you go to 1mm, you can largely get rid of this problem, and you get most of your signal in the orbital frontal sinus. Good shimming is important. Better shimming is coming online. I think it's a very exciting area of research. Thinner slices, I mentioned, takes more to cover the brain. We now have the answer to that thanks to simultaneous multi-slice. Paying careful attention to slice orientation matters. Using shorter TE can also help, but remember, the bold contrast is also TE dependent, and so if you make the TE too short, you not only won't see through-plane dephasing, you won't see bold dephasing either. So what about distortion? Well, here, if we plot the field along Y above the frontal sinus, we see there's a local gradient going up and then a local gradient going down. Those gradients cause unwanted phase evolution. They wind their own helix, and we don't control them. This phase error accumulates with time. That's why it's worse in the Y direction by a factor of 100. And it can be centimeters. Here's an example of a 3mm EPI where we take a trajectory from the top down and the bottom up. The differences are that in one case, a positive susceptibility gradient creates an image compression, and in the other one, it creates an image expansion. And so when you flip between these images, you see sort of twice the effect. You really can see it quite nicely. In a normal EPI, if you go faster, you can get rid of it. So here we're using head gradients to encode faster. Standard would be about 32 milliseconds, and you can see now the thing is relaxing in Y to about the right position with a faster gradients. But remember, it's an effect that's centimeters in magnitude. You can try to correct it based on a field map. You can try to use multi-shot methods, which don't allow as much phase to accumulate, although you'll get a lot more physiological noise. You can use refocusing pulses such as 180s, and this is like a rare method. Better gradients, faster gradients, always helpful. Parallel acquisition, parallel imaging has been our main defense against this though. And this, we simply go faster by leaving out lines. So now we're traversing KY twice as fast and we get half the distortion. Of course, we get this folded image, and Sense unfolds it using the sensitivity maps of the coil. Grappa fills in the missing line of K-space using the coil. It's easy to see how Sense works. If you have a pixel and you fold it, then the final pixel will be the sum of this yellow pixel plus the orange pixel that superimposes on it. And you end up with two equations and two unknowns. If you have two different coils looking at the problem, you can solve that on the back of an envelope for each pixel. That's how Sense works. If you have 5 coils, then you have 5 equations and 2 unknowns, and you have a slightly more robust inversion of the intensities, and you can solve for the unknowns a little bit better in the presence of noise. In the K-space picture, you have this missing K-space point, and you need to use the coil sensitivity patterns to generate that factor of e to the I delta kx between existing lines. And we use the fact that exponentials behave like this, so we just need to basically approximate that e to the I, measure the e to the I x, and then approximate e to the I delta kx from the coils. And we can do that by using the fact that when you have a bunch of coils, you can either add them up like that, or you can add them up as sort of sine waves and generate these e to the I kx terms. So how you add them up is basically critical, and the Grappa method actually adds them up from all the coils and from several adjacent K-space points to get a better estimate of that missing point. And in the old K-space picture, we would march across K-space laboriously, one point at a time. And in the sort of new, let me march across, it's very time consuming. In the new K-space picture, we think about it as an encoding ball marching across K-space and say filling in 3 lines at a time, going 3 times as fast. That encoding ball comes from the RF coil, the ability of the RF coil to synthesize those delta Ks and fill in the adjacent points. And the bigger the ball, the more you can accelerate. That just means the higher spatial frequency contents that the coil has. The penalty is, of course, that you're missing data. There's a square root of R penalty, and there's also the so-called G factor penalty from noise enhancement during the matrix inversion that when you're solving those simultaneous equations. So we keep track of this G factor map. That's the one we can deal with. And that's where building better coils come. And you find that with a good coil array, you can get up to about R equals 3 or 4 with a 32-channel coil. And here's an example just showing what it does for distortion, a very old example, showing how R equals 4 really helps with that frontal lobe distortion in the CPI image. And now this 1 millimeter isotropic has pretty much become possible with the 32-channel coil. And this also allows us to do the 0.75 at 7T. We absolutely would not be able to do this without parallel imaging. I just want to end with a mention of a new method of accelerating in the slice direction. This is actually a very old method. It's more than a decade old that this was proposed and done, actually. You take, say, 3 slices simultaneously. Then when you march through the brain, you, of course, cover it 3 times as fast. Use a coil array to unalias them because you get pancaked images like this. And the reason this sat on the shelf for a decade and a half was because it's very hard to unalias that image. Those alias pixels are about 3 centimeters apart, and so the coil information is not changing on that scale. And you get what essentially means a very high G factor. So I think, in my mind at least, the breakthrough that made this work out for us was done by Callan Setzenpop, who showed that you could apply the Kuiperania technique of shifting every other slice of the EPI stack. So now the alias pixels are half a field of U and Y and 3 centimeters in Z. They're actually further apart than a rate 2 sense, and it becomes a lot easier. The G factors are something like 3 times smaller, and you can then unalias a slice with a below 10% penalty. And the other thing that was underappreciated by us and others was that there's no square root of R penalty. You're not leaving out k-space lines, you're not leaving out samples, you're sampling the signal from all three slices at the same time. It's sort of like volumetric imaging. You actually get a square root of 3 enhancement. You get more data per unit time, 3 times as much in this case, and that's a square root of 3 advantage in sensitivity rather than a square root of 3 penalty like in normal parallel imaging. Well, we can really push it with functional imaging and get up to 10 or 12 slices. More common is maybe 5 or 6, and this allows us to really speed things up, like I mentioned before. And it also allows us to the first time to cover the whole head in a reasonable amount of time. It takes about 120 slices to cover the head at 1 millimeter. That's about 10 seconds. That wouldn't capture the resting state fluctuation band. Now we can do it in less than 3 seconds. So with that, thank you for your attention. I'm happy to take questions afterwards since I ran a little bit late, I think.